Today we are going to learn how to obtain stress concentration for a plate. Now, before going to our stress concentration, let us know what is the stress and how the stress concentration is occurring, and what are the factors that affect the stress concentration, and then we will go for modeling for the stress concentration using ABAQUS. So stress is your force by area. So if we have a bar, we have a bar like this, and if we apply some load here, and this side we used to make fixed. So force by that cross-sectional area is your stress, which is denoted by sigma. Now, if we have a bar like this, we see that how the stress is flowing. The stress flow, you see how the stress flow, you'll observe that how the stress is flowing in this member due to the applied loading. You'll observe that there will be some stress concentration this end, and thereafter you'll observe that stress is basically following like this. Stress is following like this. And after some distance, you'll observe the stress is uniform in this zone. Now, probably you can recall that while doing some tensile test, we used to measure our data. So, why we used to measure in this middle zone? Because in this zone, stress used to be uniform. And in this case, and in such cases, we will observe that failure of the material used to occur either in this middle zone or near the support. Many cases you will observe there is failure in the near the support because stress used to be high here. Okay. And in such cases, we used to reject the sample. We used to reject the sample and we used to consider those samples which basically fell in this zone, so that we make sure that stress is uniform here, and whatever the data we are measuring here, the data is coming due to your uniform stress in this zone. Now, if you consider your dog bone sample, in the dog bone sample, you will observe that we used to have a cross section like this. We used to have a cross section like this. Have a cross section like this. So now, if we apply load here, we'll observe the stress basically we should follow like this. Stress is to flow like this, and in this zone, we used to have uniform stress, and we used to measure the data here. Cross section like this. Okay, and if we do the testing, if we have a cross section like this, and if we do the testing, you will observe that many cases the failure is occurring in this zone. Many cases the failure is occurring in this zone because there will be huge stress concentration in this zone because of the change in the cross section. This is your A and this is your small a. There is a sudden change in the cross section. So stress concentration will be higher and material will fail in this zone. Okay. Now you will observe that we used to make a dog bone sample. We used to test it. So in the dog bone sample, what we used to do? We used to do the smooth transition like this, and we used to do the testing. So once in the dog bone sample, what we used to do? We used to fillet it, or you can say we used to make that change in the cross section in a smooth manner. We used to change the cross section. We used to make the change in cross section in a smooth manner, so that stress flow will be uniform in this zone, and the stress concentration that was occurring, we used to minimize the stress concentration here, and we can avoid the sudden failure in this zone. So what we have learned, that stress is basically your force by area, and stress concentration used to occur when there is a sudden change in the cross section. Now you'll observe in many design or in many analysis cases, we need the maximum stress. So that we can safeguard our structures. We can apply some factor of safety and we can design our structures. we can find that maximum stress by applying some factor. That factor is basically known as your stress concentration factor. What is the stress concentration factor? Stress concentration factor is your maximum stress divided by your average stress. The average stress that is occurring in this zone. Okay, that is known your stress concentration factor K. So what we are doing here, we are basically simplifying our analysis procedure. Once we know that what type of hole we have, whether we have circular hole or we have an elliptical hole, what type of hole we have, depending on that, we can find that what is the stress concentration factor. Once we find what is the stress concentration factor, you can find our maximum stress, which is our primary interest for design, so that we can apply some factor of safety there. Now again, you will observe, though stress is basically depend on the material property. Stress, that is your stress is equal to force by area. Okay, the developed stress in the structures that also basically depend on that your property of the material, that is equal to here. The stress is basically a force by area. Again, how much stress will develop, how much stress, this is your applied load, you can say applied load or applied stress. Okay, this is your applied stress. If sigma is equal to P by A, in that case, this is applied stress, and stress developed in the structures that will depend upon your how much elongation is occurring and what is the modulus of elasticity. So this part is your property of the material. So though stress is a function of material property, stress is a function of material property, but the stress concentration factor, is a function of geometry and the type of discontinuity we have, whether we have a circular hole, whether we have an elliptical hole, or we have a connection like this. So basically what type of discontinuity we have and what type of geometry we have. Geometry in the sense how much width of the plate we have, how much diameter of the hole or cutout we have. Depending on that, we can have our different stress concentration factor. So stress concentration factor is basically function of geometry, not the function of material property. Stress is a function of material property, but stress concentration factor is a function of geometry and what type of discontinuity we have. Okay. So now, if we have a plate and if we make a cutout like that, we will observe that stress is very high in this zone. Stress is very high in this zone. If you have a plate and you are applying like load like this, you will observe the stress is very high in this zone. So here you can observe that stress is concentrating in this zone. Now, if you want to plot, you will observe that stress, the magnitude of the stress will be high here, magnitude of the stress will be high here, like this. And if you go away from the opening part, you will observe the stress is basically changing like this. Stress is basically changing. Basically, you will observe that the stress concentration, stress basically is coming like this. This is the red part, is that magnitude is high here. If you see the magnitude, and if you plot this red magnitude, this one 2.73, and then if we plot the green one, 1.55, okay, 1.55, here 2.73, and here blue one is basically something nearly 1.37, like that. If you plot that value, you will observe that stress will be like this. It will be like this. From this side also will be like this. Okay, so here what we have seen, that stress, change in the stress, if we have a plate with a circular cutout, and if you apply the load, this circular part will be elongated and it will look like ellipse. That's fine. And here there will be high stress concentration, and if you go away from here, you'll observe the stress, magnitude of the stress basically varying like this. Magnitude of stress is varying like this. This is basically, this colorful pattern is showing what are the different kind of stress we have. Okay, so if we plot the magnitude, it will look like this. So this is what all about. This is all about stress concentration and that factor affecting the stress concentration. Now here, if we Now here we'll see what is the stress concentration factor for elliptical cutout, and next we'll discuss what is the stress concentration for a circular cutout, and again we'll discuss how stress concentration is affected by our change in the cross section. So here, if we observe that if we have a plate and we cut out, in that case, our stress concentration factor can be written like this. Stress concentration factor K, that is equal to maximum stress that is occurring in this zone, and average stress that is occurring here. Average stress basically the total load P divided by W minus D diameter of the hole, D diameter of the hole into T. That is your average stress, sigma average. Okay. Now, if you know average stress and if you know what is the stress concentration factor, then we can find how much stress is occurring here. Okay, so if we have a plate with elliptical cutout, in that case, stress concentration factor we can write as a 1 plus 2b by A. So B here, your B here, basically 2b is here, your minor radius of the ellipse, and 2a is your major radius. Okay. Now stress concentration factor K, that is equal to 1 plus 2b by A. Now if it become a circular, in that case you'll observe that your B is equal to A. Okay. And if you put, you'll observe that if you have put that B is equal to A, so this will get cancelled out, there will be 3. So stress concentration factor will be 3. So here what will happen if we have a plate with circular cutout, like this, in that case your maximum value of stress concentration factor will be 3. Maximum value of stress concentration factor for a circular cutout will be 3. Okay, now here if we concentrate on your, if we consider stress concentration factor with elliptical hole, that again can be simplified like this. The stress concentration factor for elliptical cutout can be written in this form, that is equal to 1 plus root under A by rho. Root under A1 plus root under A by rho. Okay, so A is here, that is half of your major axis, and rho is basically local radius. Rho is basically local radius of the curvature at the foot of the elliptical hole. So this is basically your rho. So now here we just see if the value of rho is small, then we used to have a high stress concentration factor. If a value of rho is very small, then we'll have a high stress concentration factor. If value of rho is high, in that case, high like this, in this case, we can have a low stress concentration factor. So high stress concentration factor, that means we will have a high stress in this zone. Low stress concentration factor means we will have a less stress that is concentrated here, and that will be low. Okay, so what we have learned, that for elliptical cutout, stress concentration factor is like this. Okay, that is again property of our geometry, not the property of your material. Stress concentration factor is a property of the geometry of the plate. Again, we have learned that stress concentration factor will be high if we have a low local radius of curvature. In that case, our stress concentration will be very high. Okay, so we have learned that our stress concentration factor is independent of the material property and is dependent upon the property of the geometry, and also depend upon what type of discontinuity we have. If we have a local curvature, if we have a local radius of curvature of low magnitude, then we'll have a high stress concentration there. Okay, so basically the size of R, or basically size of rho, the size of rho of the discontinuity decreases, then stress concentration will increase. So basically, if we have a small local radius of curvature, okay, in that case, a higher rho, in that case, if you have a higher value of this rho, in that case, our stress concentration will be low. Okay, now if we so this again this part again this theory, the theory that we have discussed here, basically for infinite plate. This theory is basically infinite plate. Now in real life we used to have a infinite plate in the sense if you have very large plate and we have a small hole cut out there. In that case, this theory is very well suited. Okay, infinite plate in the sense if you have a very large plate, but if you have a finite plate, okay, we have a definite length of the plate, definite width of the plate, definite thickness. In that case, we'll observe our stress concentration that is basically depend upon the ratio of D and the W. Stress concentration can be written in this form. So here again, you just see that what is the diameter of the cutout, what is the diameter of the cutout, or what is the width of the plate. Depending on that, our stress concentration factor is to vary. Okay, so if we have a finite plate where we have a finite length of W, finite length of the W, in that case, our stress concentration factor can be written in this form. Again, you can see that if we know what is the value of your D by W, the value of D by W, from this graph, you can have the data. So here, if you plot it, you will get the value as your 2.51 like this, nearly 2.5. Stress concentration factor will be 2.5 like this. Okay, and from that we can find what is the maximum stress occurring in this zone. Okay, now if you have a section, rectangular section or circular section in which there is a sudden change in the cross section. If you have a rectangular section or circular section and there is a sudden change in the cross section, in that case, stress concentration factor is to vary in this form. So again, this stress concentration factor is to be function of R by H as well as your W by H. R by H basically R here, basically R is here, your local radius of curvature. R is here, local radius of curvature here. Okay, so stress concentration factor is to depend on the factor of R by H and ratio of W by H. Okay. Now, if you know what is the R by H for you, and if you know what is the W by H for a particular sample, in this case, you can find the value of stress concentration factor for your plate or for your sample. And again, for this case also, maximum value of stress concentration factor will be 3. For this case also, maximum stress concentration factor will be 3. The maximum value of the stress concentration factor will be 3. And that value can be reduced if we have a smooth curvature here. If you have a smooth curvature here, then we'll have a reduced value of the K. Now question is that how to obtain the K experimentally? How to obtain the value of the K experimentally? How we can obtain it through some experiment? Use photoelasticity. In the photoelasticity, what happened? You used to have a sample. We used to have a sample, and we used to stress it, and then we used to pass a monochromatic light. We used to pass a monochromatic light. So in the monochromatic light, we used to have a single wavelength. That is why it's called a monochromatic light. It should have a single wavelength. When it passes through a medium which is under stress, in that case, it is to create different. It is to create different wavelength. It is to create different wavelength, and that is to reflect as a change in color. That is to reflect in change in color. Okay, so in the photoelasticity, we also can find what is the pattern of the stress concentration. Now, if you place some strain gauges here, okay, if you place some strain gauges here, you can measure the stress that is occurring here, and if you place some stress here, the strain gauges here, and here, you can measure the stresses and we can plot it. Okay, so one is you're using your photoelasticity. But again, in that case, that material should be transparent so that light can pass through. And if you have a very solid material and it is not transparent, in that case, you have to rely on your strain gauges. So if you have a plate and you just place strain gauges here, 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 and here, some different distance, and you measure the strain, and you know that a strain is related to stress like this, and we can find the stress. So if you have a strain gauges, you can measure the strain, and from there you can convert the stress and you can plot it. It will come. If you have a circular cutout here, the stress will come like this. Okay, so we have a photoelasticity test. We have a strain gauge that we can measure the strain, and from that we can find the stress, and from there we can find the stress concentration. Or in some brittle material, we can use brittle coating method to find the stress concentration. So these are the way through which we can find our stress concentration factor through some experimentation. Now thing is that these processes are very time consuming, laborious, and costly. These processes are time consuming, laborious, and costly. So alternatively, what we can do nowadays, fine element method is developed very well. And if we are able to model it in some fine element software, and if we see, you can have very reliable data of your stress concentration, and from there we can find the factor which you can further use for your design purpose. So here we have alternate way, that is your fine element method, but that is not experiment method, that is your numerical method through which we can find the stress concentration. Okay. Now here till now what we have discussed, that what is the stress, what is the stress, and affecting it, and how we can find it. Now here we will discuss how the stress concentration is affecting a ductile material, and then again we'll discuss how the stress concentration is affecting your brittle material. How a ductile material is behaving under stress concentration, and how a brittle material is to behave under stress concentration. If you see a ductile material, and if there is some stress concentration, you will observe that stress concentration is neglected. You will observe the stress concentration, the effect of stress concentration is neglected in case of ductile material. So what happened if we have some material? So here initially there will be some stress concentration in this zone, and this zone material, the material here, which is here, will reach to your yield value first. You will reach to real yield value first, and once the material is to yield, you'll observe that in case of ductile material, we used to have a plastic flow. We used to have a plastic flow. So what happened here, when the stress used to, when the stress acting here, the stress develop here is yield first, then nearby material also gradually reaches the yield value. Again, further increasing in the load, lead to the yielding of full cross section. So what are the stress concentration was developing here after yielding? What happened, that used to mitigate, and whole zone used to yield. Okay, so whatever the stress concentration was occurring here, that is to mitigate after some times. So since it is to mitigate and it is to distribute throughout that whole cross section, whole effective cross section, so stress concentration never become a burning topic. Stress concentration for a ductile material, stress concentration never become a big problem. Okay, now if we come to brittle material, you will observe the brittle material. You will observe, if you try to plot that failure of the brittle material and the stress develop in the brittle material, you observe that initially strain used to change gradually, stress strain behavior it will change gradually, and there is sudden failure like this. Okay, so brittle material, what happens? Stress concentration become a big factor. So in ductile material, stress concentration is not a big factor, but for your brittle material, stress concentration it become a big factor, because once it reaches that maximum stress, once it reaches that air failure stress, thereafter suddenly crack is to appear, and the cracks propagate very suddenly, and there is to failure of the structure. So concentration become a big factor, and here the stress concentration, the stress that was developing in that zone, never get a chance to mitigate. Okay, never get a chance to mitigate, because once it reaches that ultimate stress, suddenly failure is to occur, and stress do not get a chance to mitigate. Okay, so in case of brittle material, stress concentration is to be a big factor. Okay, be a big factor. Now here in this class, in this laboratory class, what we are going to do, we are going to model a plate that is made of our steel, and that your young modulus is 200 GPa, Poisson is a 0.33, and this is that geometry it is there, and this 100 Newton load is applied here. So what we are going to do, we are going to find the stress concentration factor for this plate. Okay, we are going to find what the stress concentration factor for this plate. So we know what the average stress is acting here, and if we perform finite element analysis, we can find how much maximum stress is occurring here, and if we take the ratio of it, we can get our stress concentration factor. Okay, and we can verify with our analytical model. So this part we will do first. Here again you just see we are doing linear analysis. Okay, so here we are learning basically how to model it. Next, what we can do, we can change the material property. You can see. So what we can do as a home exercise, here we will learn your linear analysis. Then we will change the material property of the material property. We will change the material property of this plate. First, we will do the nonlinear material property for ductile material, and then we will give nonlinear material property for brittle material, and we will see how the stress basically is changing and how the brittle material and ductile material is behaving due to stress concentration. Now, one more thing you have to keep in your mind, that ABAQUS do not have any unit systems. If you are using SI unit, okay, then you can use all the dimension in meter or millimeter. Okay, so either you follow these unit systems or you just follow these unit systems, you can get similar result. Okay, so best idea, you can use this parameter. All force are in Newton, all dimension in mm, and whatever the stress you will get, that you will get in your MPa, and you can directly correlate it. Okay, so here what we're going to do now, we're going to model this plate in finite element software, that is our ABAQUS, and we'll see how stress is behaving, whether you're getting this type of pattern or not. So initially we'll learn for linear analysis, then we'll change the property for our nonlinear data. Now we'll change the property for nonlinear analysis. Next we'll try to do nonlinear analysis by changing the material property. And as homework problems, we'll do these problems. Here we'll have a multiple hole. We'll see how stress concentration is to occur here and how much stress concentration is occurring, and at the end we'll try to justify the result here. Whatever the result is coming, we'll try to justify it, and this part also we'll try to do that. Your one bar is there and there is sudden change in the cross section like this, and this much load is applied there, then how much stress concentration is occurring and how the factor R, or your basically local, is affecting our result. So let us go to our ABAQUS model. Let's see how we can do it.